Okay. Let me review a little bit about what we have been learned. Okay. Okay. Let's see. We have some of this one integration method, right? And this was direct integration, right? Direct integration. For this slides, as well as we do exact equation method, right? So and some specifics. This one we cover first order, right? First order, right? And time varying as well as time invariant, as well as time varying, right? And you have some method about this one, right? This one is a form of equation. Look at this one. You have this one. Okay. This. And you have this one as well. This one communication, also this one. Sometimes we call this one other equation, right? So this form is first order anyway. You have this form. You can do by using what we call exact equation method. Okay, and the other one with this method is the exact equation, and the other one is this method, right? This one. Quadratic equation, sorry. This one called quadratic equation. This one, another method, we try to use phi to f factors. It's like an exact equation, or sometimes you say like a integration method, integration factor, and something like that. Yeah, but not exactly the same. But anyway, you see this one, another method. We can use exact equation, right? Or you can use this one, phi f, this one, to multiply this one, to multiply original equation, so that you can have solution this one. Okay. So in this case, the solution of this one is this one. Right? We do have this one based on initial condition. Right? This one. Something like homogeneous, different from particular solution. Right? This one. Okay. So there are two ways. In this case, you have to find f. F equal to e to the h. Right? H is equal to what? Integrate p x dx, right? This one, right? Okay. You can find f, you can multiply it. You can prove that this one it is. Okay. So it's something like e to the this one e to the minus h multiply e to the minus h integrate e h r e dx, right? Okay, this is another way to do it. Okay. Okay. And we do. Okay. Right. So for this one, right? We do concentrate on first order, right? This one integration method. And it's cover time invariant as well, time varying as well. Okay. So next for the second order, we reduce a little bit because you see for higher order when you have let's say when you have as I told you that linear system we have some we can do with integration method right for linear system time invariant this is the most easiest one. Okay, easiest one, and you see quite a lot in the industry anyway. Okay, the other one is this one, system but time varying. This one are more difficult, much more difficult. So we concentrate just only for first order in this case. Right, this one. Okay. If nonlinear normally is quite difficult to solve. We don't have any. These two we do have some general method. Right. This one. For nonlinear, no general method. It depends on the equation. So in that case, it's quite difficult to find analytical solution. Difficult. Okay, so sometimes we do with the numerical method to find analytical solution. See, you have some method as well as you can obtain analytical solution from symbolic map, right? From symbolic map, analytical from symbolic map. But it's not guarantee you're gonna have solution. Not guarantee anyway. Okay. If you cannot find an analytical solution from the general method or an analytical solution from the symbolic map, you can do also from numerical method. Numerical method, right? Okay. So sometimes we call graphical method. Graphical because you have graphical output. Right. Okay. See some of this one. Okay, you can have this. Right. So, but numerical method, I give you two methods. One, if you use ODE 4-5, right? Actually, there are more than 4-5. There are 2-3, 1-3, 1-1-3, 2-3, whatever. But I will give you some some characteristic of some of these method anyway. The other one is you try to use discrete approximation. Right? Discrete approximation, right? Look at this one. For example, let's say you have this one, right? Discrete approximation from this line. You see this one, right? I give you some example of this one. Okay, this one. Okay, this one. Okay, this one approximation. This one, right? By using numerical solution, sometimes we call this one is discrete approximation. Right? This one. Okay, so you have derivative, right? You go to this one, approximate. this one, right? X delta x minus x y, sorry, y x plus delta x minus y x equal to delta x. If delta x approach 0, that is approximation of this derivative, right? We call this one Euler forward approximation. Sometimes you have this one as well. Okay, so you have this one as well. You can have this one, right? This one, x minus delta x. In this case, delta x, right? This one. I also mentioned this one as well, but this one go backward. Okay, it's an approximation. It means that, right? You want to solve for this one. You convert this one to this one, right? So you substitute this one by this one or by this one, and you find the solution, right? Actually, both of them are different because it's approximation, right? It will be very close if delta x approach 0. It will be very close anyway, both of them. There are another method as well. This one forward, backward. They do have another method, triangular method, trapezoidal approximation method as well. But I won't say now. I will give you now. Just give you forward approximation, right? So this one, if you convert this one to this, and you convert this equation to this equation, right? Right. This one is differential equation, right? This one we call it differential equation. This one we call different equation. We call different equation. Right? We call this one, right? So in your assignment, you have to perform this one as well, right? Your assignment, okay, you need to perform this one as well to do approximation, right? By using numerical discrete time approximation, right? Discrete time, see, in our if t is our independent variable, there will be times, right? Okay, so try as well. So for numerical solution, you have, right? You can use ODE 45 from MATLAB. I will explain to you later after midterm how this comes from. And this one is discrete time approximation. Discrete time, right? Approximation, right? By using approximation, by using Euler forward approximation, right? We call this one, right? So I also give you some example. This one, right? You want to solve for this one. You see, this is a program. You need to write the program because to solve this different equation, you see, you have these different equations. You have to obtain this different equation first. Okay, and after that, you just do solve it. You have graph here. If delta x is very close to 0, you see the solution from your calculate, from your analytical solution, from exact equation compared to this one, very close. If delta x is larger, you see you have some lag between this one, right? Between step interval and for analytical solution, See, okay, so we have this one. Okay, actually, this one is first, right? So we switch a little. Okay. This one, this is we start from this one, so this is approximation. No, this one approximation. Approximation. This one is from analytical solution. Analytical. How come I know? The blue one will be the first one you draw. The red one will be the second one. You see, we draw this one first. You see, you plot this one first. This one is you use this approximation. So this approximation, and the red one is second one. Is solved by using this one. And plot this one. Okay, you have this solution. You want to plot this one. See, you have this equation. You want to plot this one. Okay, you can plot this one. Okay. So this one you have to try in your assignment number 4 as well. Okay. Okay. Right, this one as well, you see. This one we use backward. Either backward, right, this one. You see? Same. You use either backward. You have some, if the other x or the other t is very close to 0, the approximation are very close to the exact one. Okay? Okay. That's okay. Okay, we'll read this one. Okay. So when you have this one, so for second one, now second order and arbitrary order, right? You have second order. We just limit on linear, and if linear time invariant, right? And linear time varying, right? Linear and time varying, but this one only Cauchy order, Cauchy only, right? This one. Similar to this one for arbitrary order. Right? We cover also these two as well. Right? If you have linear time invariant, normally we can solve this one. We have differential equation, right? You can solve by split into homogeneous solution and particular solution, right? You solve homogeneous solution, we normally assume solution in this form. If t is an independent variable, we have this one, right? For this one, we obtain what characteristic equation, and we obtain lambda, which is eigenvalue, right? If time varying, this one, we assume this one, right, instead, right? This one to solve the problem, to obtain the characteristic equation, right? For second order system. Higher order system are the same. They are the same anyway. Compare second order and higher order system for homogeneous. With these two, we are do the same. Only this second order we have two eigenvalue, right? But this one is more than two eigenvalue, right? This one The rest, the method are the same. As I mentioned, if you have linear system, we have general method, right? This is called general method that to solve differential equation, right? Okay. So if the most difficult one is if you have not homogeneous now, you have external force, right? If you have external force now, that are more difficult anyway. Okay, so same, external force is mean that you assume y particular, right? To solve this one, you just assume y particular form. Y particular can be assumed based on solution, homogeneous solution, and also input. Sometimes we look at homogeneous equation. Sometimes we look at the external input. Right. So assume YP, right? Okay. So today I will show you more general method how to assume YP, right, to solve. Okay. Okay, so let me show this one. Okay. Look at this one. This one. Okay, and this one. We have, look at this one. You see, when you solve this one, non-homogeneous particular solution, right? Okay, so you have Rx, right? You have Rx, right? Let's see if you have this equation. Let's see. Let's see if you have this one. See, this is actually this is a second order system. Right, second order, right, with external input.